To get a digital entity from point A to point B, you have to solve one of the oldest problems in computer science, finding the absolute shortest path. Whether it's an AI enemy in a video game or a GPS routing a car through a city, the core challenge is exactly the same. For decades, the gold standard for solving this was Dijkstra's algorithm. It is a method guaranteed to find the mathematically perfect route every single time. As we look at this animated grid, you can see exactly how it works. The algorithm calculates the distance from the starting point and expands outward in a perfect continuous circle. It treats every single step in every possible direction identically. Because this method only measures the cost of where it has already been, it has no concept of where it is going. It explores the cells behind it and to the sides just as aggressively as the cells moving forward. This makes the algorithm entirely blind. It calculates the cost of hundreds of useless dead ends, heading in the exact opposite direction of the destination, only stopping when it accidentally bumps into the target. In massive computational spaces, demanding blind mathematical certainty drains a catastrophic amount of processing power and memory. That physical hardware limitation hit a hard wall in 1968. Researchers at the Stanford Research Institute were trying to make a mobile robot named Shaky navigate a physical room on its own. Its onboard hardware simply couldn't handle searching the environment in a blind 360-degree circle. The programmers needed a way to give the algorithm sight. They had to figure out how to pull the search directionally toward the target without losing that ironclad mathematical guarantee of finding the shortest route. The solution required a delicate balancing act. They had to maintain an exact record of the steps they had already taken, while simultaneously making highly educated guesses about the steps they still needed to take. That solution is the AStar algorithm, and the secret to its efficiency is a single new variable called the heuristic. The total route cost, f of n, takes the exact known cost, g of n, and adds a mathematical estimate of the remaining distance, h of n. This estimate acts like a magnet, actively pulling exploration aggressively toward the target. But this guess has to follow a strict mathematical law known as admissibility. To guarantee the shortest route, the heuristic estimate must never be larger than the true remaining distance. If it overestimates, the system breaks. This means developers have to choose their guessing formulas carefully. For a strict grid where characters only move in 4 directions, they use the Manhattan distance, which simply counts the blocks. But for an open environment where a unit can move at any angle, they use a straight-line Euclidean distance. The efficiency of AStar relies entirely on keeping those two numbers strictly isolated. The exact data of the past must never be tainted by the estimations of the future. When you try to code this yourself, that separation is incredibly easy to mess up. There is a notorious logic trap in AStar that developers trigger all the time. Here, a node has a total score, f. A fatal mistake is adding the next step's cost to f instead of the historical cost, g. Since f includes the heuristic guess, this compounds it twice, breaking admissibility by overestimating distance. When the math breaks, the algorithm becomes delusional. It takes erratic, sprawling paths that burn through memory without ever getting closer to the goal. The fix requires rigorous accounting. Programmers must maintain a completely isolated ledger that only tracks the exact past. The future guess is only ever applied at the very last moment, right before ranking the available options. Corrupt the mathematical boundary between what you know and what you guess, and the entire navigational system collapses into inefficiency. But when the code is clean, the result is incredibly sharp. As we watch this search pattern, you can see a tightly focused cone locking directly onto the target, entirely ignoring the vast empty space behind it. Compare this directional movement to the massive 360-degree circle we saw with Dijkstra's method earlier. All of that extra surface area is memory that is no longer being wasted. Once developers mastered this formula, they realized they could intentionally break the rules to gain a performance advantage. This is a technique called weighted AStar. By multiplying the heuristic so that it actively overestimates the distance, you sacrifice the guarantee of a mathematically perfect route. In exchange, the algorithm runs at lightning speed. It is an ideal trade-off for calculating the paths of hundreds of background characters in a crowd, where a good enough path is all you need. AStar is a flexible, programmable framework. It allows engineers to dial in the exact boundary between absolute historical truth and highly educated guessing, building the foundation for the massive, dynamic digital worlds we navigate today.